Welcome to the Explainer. Today, we're diving into something really fascinating, the literal physical infrastructure that's quietly powering this massive AI revolution we see happening all around us. We constantly hear about large language models and incredible algorithmic breakthroughs, but what we almost never talk about is the sheer physical toll these digital miracles take on the data centers housing them. So today, we're going to fix that. 10 kilowatts. Think about that for a second. That is the staggering amount of heat that modern high-end AI servers are generating right now, per single server. Seriously, 10 kilowatts from just one unit. This isn't just some minor technical hurdle. It's creating a critical physical crisis for data centers globally. I mean, if you can't remove that heat, your massively expensive AI chips will literally bake themselves. So how in the world do we solve this? Okay, let's dive into this. Here is our roadmap for today. First, we'll look at the AI heat crisis. Second, the anatomy of liquid cooling. Third, scaling to the rack. Fourth, flexible server architectures. And finally, number 5, the massive green payoff.
All right, part 1, the AI heat crisis, hitting the thermal wall.
We really need to establish exactly why the tech industry is hitting this massive thermal wall. It basically comes down to a huge mismatch. See, for decades, data centers just used CRAC units. That stands for computer room air conditioning. Essentially, they're just giant air conditioners blowing cold air down the aisles. But modern AI needs, they are completely off the charts. We're now packing multiple CPUs and GPUs into single servers, which drastically drives up the thermal design power, or TDP. Simply put, air just cannot absorb and move that much heat fast enough anymore. Which brings us to part 2, anatomy of liquid cooling, hardware solving the heat. Since air is totally failing us here, the solution actually has to start directly on the silicon. But we're looking at our Supermicro CPU and GPU cold plates. Instead of using a bulky metal heatsink with a fan just blowing air around, these plates sit completely flush against the chips. And inside them, they have these micro-sized channels where liquid flows directly through, absorbing that intense heat with ultra-low thermal resistance. It's a brilliant piece of engineering, specifically designed to eliminate hotspots directly at the source. Now, once that liquid absorbs the heat from the chip, it obviously has to go somewhere, right? It gets handed off, kind of like a relay race, to the coolant distribution manifold, or the CDM. You can think of the CDM as the vital plumbing for the server rack. It supplies the frigid liquid to those cold plates and then safely returns the hot liquid away from the servers. And because data centers are absolutely mission critical, these use quick disconnect, flexible hoses with single-handed zero-drip connectors, meaning operators can service a liquid-cooled system totally safely without any fear of spilling water onto millions of dollars of computing equipment. That would be a total nightmare, obviously. So all of that plumbing leads right back to the coolant distribution unit, or the CDU. This is really the powerful beating heart of the whole system. Depending on how it's configured, a single Supermicro CDU can pump up to 250 kilowatts of cooling capacity throughout the entire rack. Plus, it features hot-swappable, redundant enterprise-grade pumping and power modules, so if something fails, the system stays up. Operators can even use an integrated touchscreen to monitor and optimize power consumption, all while managing a smart anti-condensation strategy to prevent hardware degradation. All right, let's look at part 3, scaling to the rack, high-density compute. When we actually scale these components up, the sheer density this technology allows is just staggering. Because liquid cooling is vastly more efficient than air, you don't need those massive gaps for airflow anymore. You can literally stack computing power right on top of itself. To give you an idea, Supermicro's flagship architecture lets you pack up to 72 NVIDIA Blackwell GPUs into a single 52U rack. That is an absolutely astonishing amount of high-performance computing happening in a remarkably small footprint, and doing it all without overheating. Let's follow the macro journey of a single water drop here. The cold liquid enters the server rack from the CDU. It travels to those cold plates to absorb that massive thermal load. And then the warm liquid is piped completely out of the server environment. It travels all the way out to a cooling tower, like a dry cooler or an evaporative tower outside, where the heat is safely exhausted to the outside environment. Then the liquid returns chilled, and the whole cycle repeats. The heat is pulled entirely out of the data center. Moving on to part 4, flexible server architectures, adapting to workloads. Now, you might be thinking this is a one-size-fits-all thing, but this direct-to-chip cooling actually integrates across a ton of diverse architectures. For example, systems like the Big Twin are optimized for multi-node density and storage. Or you have the Superblade, which utilizes shared components to reduce the footprint. Then there's the Hyper, offering flagship performance with highly flexible input/output options. You can even run a Flex Twin system purpose-built for super complex, high-performance computing workloads. And of course, there are GPU-optimized architectures designed for maximum acceleration when dealing with large-scale AI training and LLMs. So basically, the cooling adapts perfectly to whatever tool you actually need. And finally, part 5, the massive green payoff, efficiency and savings. Get this, by switching from traditional air conditioning to direct-to-chip liquid cooling, data centers can achieve up to an 89% reduction in server cooling electricity costs. 89%. That is a massive operational saving just to the component level, all because you aren't running those desperately inefficient CRAC units and giant fans anymore. And when we zoom out to the macro level, that component efficiency scales up beautifully. It translates to up to a 40% drop in total electricity costs for the entire data center. Really let that sink in for a moment. You are cutting the power bill of an entire AI infrastructure nearly in half simply by changing the medium of heat transfer from air to liquid. It's a real game changer. Oh, and here is a really surprising fact that kind of gets overlooked. This also results in up to a 55% reduction in server noise. If you have ever been inside a traditional data center, you know it literally sounds like a jet engine on the tarmac. By eliminating those thousands of high-speed server fans, liquid cooling drastically improves the physical working environment for the actual humans operating these facilities. So the crucial takeaway here is simple. Data center scale liquid cooling reduces costs and increases performance. It's a total win-win. By solving this physical heat crisis at the chip level, you don't just save massive amounts of money and energy, you actively prevent thermal throttling. You see, when chips get too hot, they slow themselves down just to survive. Liquid cooling prevents that entirely, unleashing maximum sustained AI performance. I want to leave you with this final thought today. As the demands of artificial intelligence continue to scale upward exponentially, the basic physics of heat aren't going anywhere. We've seen how direct-to-chip liquid cooling provides a totally crucial pathway forward, but it really raises a major question for every tech leader and data center operator out there. As AI scales up, is your infrastructure ready to cool down? Thank you so much for joining me for this explainer, and keep questioning the technology that shapes our world.